So now let's do some examples of vector spaces. So, well, one example is the trivial vector space. So this, remember, a vector space has to have a zero vector, so the only vector, it's only one vector, is the zero vector. It's just the zero vector. And of course, we can scale. If you do, 2 times 0 is still the zero vector. And in general, if you take any number times 0, you get the zero vector. So we can scale. And the zero vector plus the zero vector. Well, by definition, the zero vector, if we add the zero vector to any vector, we get the same vector. So if we add the zero vector to the zero vector, it doesn't change it. So we get the zero vector. This is the definition of the zero vector. And so that implies that if we add these two objects, which are the only vector we have, we still stay within the vector space of the only vector. So you can check the other properties. They're very obvious because everything just gives you the zero vector. So it's kind of a trivial vector space because it's just very trivial. There's only one vector and all the operations are trivial. If you scale it, you still have the zero vector. If you add the zero vectors, you just get the zero vector. If there's only one vector, you can't do anything to it. So it's the trivial vector space. Okay, so our favorite example, our most familiar example, is just ordinary n-dimensional real space, Rn. So this is n-dimensional real space. Just like R2 is the coordinates plane that you're used to dealing with in, algebra and calculus and everything. So Rn, so here the objects of Rn, as we know, are just n tuples of numbers which describe coordinates of points in n-dimensional space. So you have like an x1, an x2, an xn. So where, of course, all of these x1, x2 are themselves numbers, and they describe the coordinates. These are like the coordinates of well, the entire tuple, so they're coordinates of a point in n space. Anyways, this should be familiar with them. So these are the objects, or the vectors. So in a vector space, they're called vectors. And we add them. We do pointwise addition. So if you, to add them, it's what you already know. If you have x1 up to xn, if that's one object, and another object, say, is y1, y2 up to yn, then that's just equal to the first coordinate is you just add the first coordinates. I didn't put commas here. The second coordinate is you just add the second coordinates. And you just keep going, xn plus yn. So you just add all the coordinates. Now because the coordinates are themselves ordinary numbers, and we're just defining addition by just adding the coordinates, we know addition of numbers is associative and commutative, so this is associative and commutative, so it's associative, it's commutative. That's good. We have the zero vector is the vector whose coordinates are all 0. That's good. And every vector has its inverse. So the inverse of a vector, we'll just write negative that vector. So if you have n coordinates, it's just, you just negate, make all the coordinates negative. Okay? And we see that, if you add, so this clearly has the right property. For, I'll just illustrate this in lower dimensions to be concrete. So if you have something like in R2, if you have x1 comma x2, if you add to that negative x1, negative x2, well, by definition, you just add all the coordinates. So you get x1 minus x1, x2 minus x2, and of course that gives you 0, 0, which is the zero vector in R2. So it has, each element has an inverse, and you can check So that tells us everything we need to know about vector addition. So that's how we define addition. And then scaling is, you already know how we scale in Rn. So scaling is just we distribute over the coordinates. So if you have n, maybe not n, but if you have x1, k, some number times, you just multiply all of the coordinates by that same number, kx2. And again, since it's just multiplication of numbers, it has to satisfy the distributive property. So you can check that everything is good. Anyways, so I just want to emphasize that. So you can go through the details if you'd like. So Rn is a vector space. Let's do another example. The set of all, say, m by n matrices is a vector space. Using addition of matrices, which you all know, so you just add all the coordinates. So it has to be a fixed dimension, so that's why they all have to be of the same type. You can add two m by n matrices together, you just add all the coordinates, and using scaling a matrix. So addition of matrices is something you already know, and you can scale, and scaling a matrix by a number. And of course that just means you multiply all the entries. By the same number. So the set of all matrices of a fixed dimension is a vector space. So, but it has to be of a fixed dimension. That's why I put that in red there. Okay. So a mini example would be like, so for example all 3 by 2 matrices. That's one vector space. Or all 5 by 5 matrices. Okay, so well, just like the Rn example, that gives you infinitely many examples. R1 is a vector space, R2 is a vector space, R3 is a vector space. So you generate infinite number of examples from, sorry, I misnumbered this, from our second example over here, Rn. So this is true for all n, so that gives you an infinite family of examples. Similarly here, we have an infinite family of examples because you can let m and n be any positive integers. And so any fixed dimension, so for any fixed rectangular array of numbers, we have a vector space. And then more examples come from certain families of functions. So we can say like all continuous functions, all continuous, say real functions is a vector space. So we have to say, so the vectors are the functions. And how do we do addition? Well, addition is just addition of functions, just ordinary addition of functions that you're used to, right? So if you have the continuous function x squared, and then you have the continuous function e to the x, then you can just add them, and that is still a function. And of course, scaling is you just multiply, you can just multiply with the function by a number. It's still a function. Multiply a function by a number. So for example, you can do 2 times, x3 plus 5x. That's still a function. And actually, we can consider certain subspaces of the continuous functions. So we can also consider like all differentiable functions, sorry, I can't write anything. All differentiable functions is also a vector space. Because if two functions are differentiable, that means you can calculate their derivatives, then you can add them together and you calculate the derivatives. This derivative is distributed over addition, so you can still calculate all the derivatives. If you multiply a function by a number, then when you take the derivative, you can pull out the constant, so you can still take the derivative. So all differentiable functions is a vector space. Say all polynomials. These 5 and 6 are special examples of continuous functions. All polynomials is a vector space. Similarly, if you consider all polynomials of a fixed degree, is a vector space. So anyways, these are the most important examples of vector spaces, at least to get started in physics and engineering. These are the spaces we care about typically. We care about Rn, that's a model for like reality. R3, it's like the world we live in. If we exclude time, matrices are incredibly important for organizing information. The collection of all matrices are themselves vector spaces. We actually know that matrices represent linear transformations, which are themselves special types of functions, and so we can actually see example 3 as being a consequence of example 4, because special types of functions may or may not themselves be vector spaces. And then we have, functions are vector spaces. So if they're continuous functions, they're vector spaces basically as long as the property is respected by addition and scalar multiplication. So if you have two continuous functions, if you add them, they're still continuous. If you double a continuous function, it's still continuous. Therefore, it forms a vector space. And similarly with differentiable polynomials and everything else.